problems facing the Rutherford model of the atom had their source in the demands imposed by classical electromagnetic theory. Classical electromagnetic theory predicts that an orbiting electron should emit radiation. It predicts that this radiation will change in frequency as the electron loses energy. Eventually, the electron will spiral into the nucleus, causing who knows what to happen. But we can see with our own eyes this prediction is false. Some atoms glow in the dark by emitting visible radiation, but they do not change color, which would indicate a frequency shift, nor do they blow up, disappear, or otherwise self-destruct. It would seem that in its attempts to describe the atomic structure, classical theory delivers us to a frontier. Beyond this frontier, the laws describing some things must be radically different from those envisaged by Newton. Working under Rutherford was a brilliant young theorist, Niels Bohr, who came to the rescue of Rutherford's atomic model. He suggested that the laws governing the motion and behavior of large bodies and particles are inadequate to explain all the motions and behaviors of atoms and electrons. He proposed that an orbiting electron, despite the fact that it is an accelerating charge, does not necessarily radiate energy. A relatively new proposal, put forward by Max Planck, who in the late 19th century had held the Berlin Chair of Theoretical Physics, provided Niels Bohr with his starting point. Planck proposed that matter, when emitting or absorbing radiation, does so not continuously as had been thought, but rather in discrete bundles of energy. Each bundle is called a quantum. Bohr knew that electrons traveling close to the nucleus in small orbits possess less energy than those moving in larger orbits. This is because an electron near the nucleus is attracted more strongly by the nucleus than one that is further away. Energy is required and work must be done on an electron in order to move it from a small orbit to a large orbit. Bohr reasoned that the energy difference between the smaller and larger orbits must somehow be related to Planck's discrete bundles or quanta of energy. This led Bohr to conclude that around the nucleus of an atom, an electron may occupy only certain precise orbits or energy levels. Bohr predicted that for the hydrogen atom, the radius of those allowable orbits was given by an equation directly related to the orbit number. Because the radius depends on the square of the orbit number, the distance to successive orbits increases rapidly. There is no theoretical limit to the number of orbits. Bohr developed another equation to predict the speed of an electron in each orbit. Most important, Bohr found a way of calculating the energy of the electron in each orbit. It's a function of the speed of the electron and the attraction between the nucleus and electron. which, as Coulomb's law describes, depends on the square of the distance between them. Using this formula, Bohr predicted the energy levels for each of the allowable orbits in the hydrogen atom. In formulating his concept of atomic structure, Niels Bohr concerned himself primarily with the simplest atom, hydrogen, which has one electron. By calculating the possible energy levels of orbiting electrons, Bohr was able to explain the specific frequencies of radiation that can be detected when hydrogen is under constant bombardment from moving electrons. In Bohr's concept, a free electron may eventually collide with an orbiting electron. Such a collision can transfer energy to the orbiting electron. The question is, how much energy must be carried by the free electron in order to knock an orbiting electron out of its orbit? What is needed is enough energy to overcome the difference between this orbit and another higher orbit. In this case, if the energy of the bombarding electron is less than 10.2 electron volts, there will be no interaction between the target atom and the free electron. But an electron of exactly 10.2 electron volts can give up all its energy to an orbiting electron in the ground state and bounce it up to the first excited state, n equals 2. The free electron will escape from the atom with zero energy. An electron is not limited to a jump to the nearest higher orbit. It can jump to a farther orbit, as long as a colliding free electron has at least enough energy to equal the difference between the orbits in question. In every case, any leftover energy is retained by the free electron. If a bombarding electron has and gives up more than 13.6 electron volts to a hydrogen atom, the orbiting electron is liberated from the nucleus, and the atom becomes ionized. The energy difference between orbits is the key to explaining the hydrogen spectrum, because electrons quickly return to closer orbits. Bohr proposed that the electron, in returning to a lower orbit, would give off, in the form of a photon, a quantum of energy that exactly equals the difference in energy between the two orbits. This photon is, of course, detectable radiation. For the hydrogen atom, Bohr calculated the energy differences between all the allowable orbits and the frequency of a corresponding photon. Just how well did Bohr's model predict the hydrogen spectrum? We'll find that out in the next program. The model was certainly good enough to be a passport for the atom to enter into the world of modern quantum physics.